Hey guys, welcome back. We're going to look today in more detail at the Sierpinski triangle and its empty regions and develop a way for thinking about its removed area, which is going to point us in the direction of some other things that we're going to study. Actually, it wasn't so much the chaos game and the Sierpinski triangle that I want to talk about for the next couple days, but they point me in that direction quite nicely. So we started here. All right, here we go. How much of the triangle is empty? Again, let's assume that we start with a triangle with area 1. It makes the calculations easier. If the area of this triangle is 1, you should be able to see that because these 4 triangles are all congruent, fitting up the inside, that the area of this first empty region is 1/4. The next 3 empty regions, all the same size, three of them, are each 1/4 of 1/4 of the original triangle, making each of the triangles this size one at a time 1/16 of the original triangle, 1/4 of 1/4. And there are 3 of them, so they have a total of 3/16 of the original triangle. Next level down, let's change colors. We come to triangles this size. First of all, let's count them. How many of them are there? 1, 2, 3, 4, 5, 6, 7, 8, 9 of them. How big are they? This is 1/4 of 1/4 of 1/4. So each of these is 1/64 of the big triangle. There are 9 of them, so they total 9/64. So far we have a 1/4 plus 3/16 plus 9/64. Next size down. 1, 2, 3, 6, 9, 18, 27 triangles that size. Oh, look at the pattern. 1, 3, 9, 27. I wonder what the next one is going to be. This triangle is 1/4 of 1/4 of 1/4 of 1/4 of the triangle. 256. Oh, look at the pattern. I wonder what the next one is going to be. Well, I will tell you, the full Sierpinski triangle, if the process were run forever, the numerators would always multiply by 3. And the denominators would always multiply by 4. And this process will run forever. The question is, what do they all add up to? How much of the triangle is empty? How do we add up infinitely many things? How do we add up an infinite sequence of fractions? This is what's called a geometric series. Geometric, not really having anything to do with geometry or shapes or anything like that. Geometric because the growth is exponential. Actually, in this case, it's exponential decay, but it's exponential nonetheless. The question we ask is, what do they add up to? And the way we analyze this is to say, let's call whatever they add up to S. And now what I'm going to do is take this equation and do some algebra with it. The first thing I'm going to do is multiply both sides of this equation by 3/4. Why 3/4? Well, 3/4 is the fraction I multiply each of these numbers by to get the next number. 1/4 times 3/4 is 3/16. 3/4 times 3/16 is 9/64. 9/64 times 3/4 is 27,256, etc., and so on and so forth. What I get now for an equation looks like this. 3/4 s equals 3/4 times 1/4 is 3/16. 3/4 times 3/16 is 9/64. 3/4 times 9/64 is 27,256. 3/4 times 27,256 is 81,024, etc., etc. Now, ignore the orange there. The orange is just kind of scratch work where I said I'm going to multiply both sides by something. What I'm going to do is I'm going to take this top equation and this second equation, and I'm going to subtract them. Just like you used to do in freshman algebra when you would combine equations with addition and subtraction. You'd subtract the second equation from the first one. So I'm going to take this equation and subtract it, again, ignoring the orange, from the first one. Well, each side presents its difficulties. Because look at this, I have an infinite list of numbers here and an infinite list of numbers there. How can I subtract an infinite list from an infinite list? Well, notice, these two fractions cancel. And these two fractions cancel. And these two fractions cancel. And so on down the line, they all cancel. Now you might think this list is shorter than this list because I've knocked one off of here. But remember, both of these lists are unending. This one's never going to run out. There'll always be one to cancel. So when I subtract this bottom line from this upper line, I get 1/4. This one presents its own trouble to some of you guys. Remember, s is equal to 1s. There's a coefficient of 1 there that we don't write. Now let's look off to the side and do a little scratch work here. What's 1s minus 3/4 s? Remember your algebra, guys. Combining like terms, you subtract the coefficients. What's 1 minus 3/4? 1 minus 3/4 is 1/4. And the s's just go along for the ride. This is nothing more than combining like terms. Don't do something silly like cancel the s's. Don't forget that that's a 1. Remember, 1 minus 3/4 is 1/4. And the left-hand sides are 1/4 s. Now, you should be able to look at that equation and know what s equals. But if you want, we can do some algebra. We can divide both sides by 1/4. Over here, the 1/4s cancel, and we're just left with s. Over here, well, 1/4 divided by 1/4, a thing divided by itself has to be 1. S equals 1. Timeout. What does that mean? That means that this s is 1. That means that this sum adds up to 1. That means that this series, which describes the empty region in the Sierpinski triangle, adds up to 1. But the area of the original triangle was 1, and the area removed is 1. That means the entire triangle has been removed. None of the triangle is left. It's all empty. Now that alone is kind of a startling result, which we could talk for days about. It has to do with objects called fractals. And if you'd like to go study fractals, there's plenty of good sources on the internet for them. Look up Sierpinski triangle, look up fractals. they often have these confounding properties like there's nothing there. All these segments are there, but the regions themselves are gone and they're empty. More importantly for where we want to go is we've learned how to add up an infinite series of fractions. When the fractions decrease exponentially this way, we have a method for adding them up. We could, for instance, take another one. We could take something like 1/3 plus, I'm going to make this up, 2/15 plus 4/75 plus 8 375. Am I doing this right? I think so, yeah. Plus, etc., etc., etc. You should see that I get from one fraction to the next by multiplying by 2/5. 1/3 times 2/5 is 2/15. 2/15 times 2/5 is 4/75. 4/75 times 2/5 is 8 3/75. Now, a fun thing to do would be just to take your calculator and add these things up until they get small and see what they get. But what I want to do is use our method to see what they add up to. Set this equal to S. Multiply both sides by 2/5. And we get 2/5 S equals 2/5 times 1/3 is 2/15. 2/5 times 2/15 is 4/75. 2/5 times 4/75 is 8 3/75, etc., etc., etc. Subtract. On the right-hand side, everything cancels except for the 1/3. On the left-hand side, we have 1s minus 2/5 s. Well, 1 minus 2/5 is 3/5. So the left-hand side is 3/5 s. We divide both sides by 3/5. Oh, I hate dividing by fractions. But don't worry, it's the same as multiplying the reciprocal. So the left-hand side is s. And the right-hand side is going to be 1/3 times, flip that over, 5/9. And we find out that all that stuff adds up to 5/9. Add these up. It's not going to happen for a while, but you should get something approaching 0.5 repeating, which is 5/9. Quiz today. I'm going to give you 2 series like this and ask you to use this method to add them up and see what you get. And then those 2 numbers will be the answer to the question. We'll talk more about infinite series tomorrow. That's the day, guys. Infinite summing. I'll see you tomorrow.